So this is our function from the previous slide. Let's actually do that expansion out. Now I have more space, so it's easier for me to write. This is kind of one way you could evaluate a recursive function. So imagine we want to do factorial of, and let me make my life a little bit easier. Let's do factorial of 4. So factorial of 4. Imagine I want to compute this. And up top I have these rules, and I want to apply these rules in order to compute the value of factorial. Well, what I would do, right, is first I start with, I need to do 4 factorial. All right, given that, look up here and look for the left-hand side that applies to me. So the first one I see is 1 factorial. Well, I'm not trying to compute 1 factorial. That doesn't apply to me. Can't use that rule, go down. N factorial. Oh, here's something I can use, right? N can be any number. So this is the rule I want to use if I want to compute factorial. So over here, right, what I would do is I would write equal, right? I'm just going to follow that rule up there, equal, and then I'll put in 4 for n, right? This is just standard math. 4 times 4 minus 1. I guess I'll write the long form there just because. And really inside, right, this becomes 4 times 3 factorial. Right, so I've taken my factorial, right, I wanted to compute factorial of 4, and I've made it a little bit simpler, right? So the factorial of 3, right, factorial of 3 is going to be simpler to compute than the factorial of 4, right? I'm making my problem a little bit smaller, right? It's still the same type of problem. I'm still trying to compute the factorial of a number, but now the factorial I'm looking for is a little bit simpler, a little bit easier to get than the one I started with. So let's say I've done this, and I need to finish evaluating this. Well, I repeat the process. I have 3 factorial, I look back at my rules, I see that the first rule doesn't apply, so then I look down at the second rule, that one's pretty general, so I'll go ahead and use that. So again, we do a rewrite, so 4 equals 3, right, that's the n over here, times 2 factorial. I won't write out the whole thing there. So I have that, not done yet. Still got a factorial on my right hand side. Just assume this is a nice factorial symbol here. I know it's not that well written. Anyways, look up at the top. So we have 2 factorial. Gotta figure out what that is. First rule still doesn't apply, right? It's still not equal to 1 factorial. It's 2 factorial. So I'll apply the bottom rule again. So I'll go over here and I'll go 4 equal 3 times 2 times 1 factorial. So I've applied that rule, right, and every time, right, that n minus 1, right, that value there that I'm having to compute the factorial of, right, it's getting smaller each time. It's getting simpler to compute each time. So now I have 1 factorial. Well, if I have 1 factorial, I look back up at my rules, and my rules say, oh, you have 1 factorial. That means you use 1, right? You don't have to do this kind of complicated thing, right? You just put in a 1. So over here I might write equals 4 times 3 times 2 times 1, right? So that's now I've written out my entire expression. So I could evaluate that, and in the end I'll get my 24. So I've computed the result of a factorial, right, using this recursive rule. So this hopefully is okay. It's not too complicated. The idea is we're just applying the same rule again and again and again to make our problem simpler, right? Until we get something that's just multiplication, and then we can evaluate the whole thing. Unfortunately, these rules aren't always easy to write or clear to write. So let's kind of look at a couple of maybe edge cases or things that might happen to us when we're trying to figure this out. So let's say I was having kind of a bad day or wasn't paying attention, and over here I had a rule like this. Factorial of 1 equals 0. So this is maybe a minor change, but you might already think to yourself, oh, something's going to go very wrong. And that's what's going to happen. So these kind of initial steps will all be the same, right? So imagine I want to evaluate 4 factorial using these rules. The first step, that'll be the same. Second step, the same. Third step, the same. Fourth step, the same. Over here, this is where I'll have issues, right? So this step over here, that's where I was applying that top rule, right? The base case rule that lets me stop with the recursion. If I have this here written, what I end up writing is this. Equals 4, 3, 2 times 0. Well, anything multiplied by 0 is 0, so this is going to end up being 0, right? So I need to be careful with my base case, right? So in this case, I've kind of done all the intermediate work right. So I've done the 4, the 3, the 2, that all worked out fine, but I messed up in my base case, right? And my base case, in a sense, poisoned my answer, right? It went back and it threw away everything that I worked hard for, right? So this is something to look out for, right? Your base case can throw away all the work you've done. A lot of times your base cases, so this one over here, for example, right? A lot of times these kind of values that are used here are going to be identities, right? They'll look like something that doesn't change what you're working on, right? So this is all in terms of multiplication. So it's very kind of natural to put a 1 at the end because that doesn't change anything, right? 1 is the multiplicative identity, right? You can multiply anything by it and you'll still get the original number out. So if you have kind of a base case that doesn't change the work you've done, you don't have to worry about it messing up stuff here, right? The issue here, right, is that everything was good up until we hit the base case. Base case ruined everything. The way we avoid that is by engineering a base case so that it doesn't kind of break the things that we're working on. If we were doing something with addition, you could think, maybe you would return 0 at the end, right? Because that won't change anything, right? If you're just adding stuff up. So kind of got to be careful there. So let's kind of X that out. So let's say we still knew what we're doing, so we would expect to equal to 1. But let's say over here that we did something again different. Let me kind of draw us off to the side a little bit. Let's say that we didn't have this -1 part. So we had n factorial equals n times n factorial. Maybe you want to try for a second on a piece of paper to sketch out what this would look like. All right, so let's try doing that. So let's say over here, right, I have 4 factorial, right? That's how I'm going to start, and then I'm going to try applying my rule to evaluate it. And I would go 4 factorial equals 4, right? N times 4 factorial. Let's try this again. Equals 4 times 4 factorial. Well, equals 4 times 4, times 4 factorial. Apply it again. 4 times 4 times 4 times 4 factorial. Maybe you can see the issue here. In this case, right, we just keep on repeating 4, right? We never get closer to the base case, right? Our problem never gets simpler, right? Every time I want to figure out what factorial of 4 is, I still have to figure out what the factorial of 4 is, right? I've essentially regenerated my original work, right? I want to evaluate this, but it appears on my right-hand side, right? So I haven't actually made progress towards figuring out what that factorial is. In fact, I've just gotten stuck, and that doesn't do me any good at all. So this is actually an example of infinite recursion, which we talked about a couple slides ago, right? So the idea is you never stop, right? Anytime you try to evaluate that right-hand side, you still have work to do, right? You still have to compute a factorial, still have to compute a factorial, still have to compute a factorial. And that just goes on and on and on, and you can never figure out what your final result is. So again, this is something that we don't want to do, right? This is also bad, right? Also bad. So let's see. Let's assume we put this back, and let's look at kind of one last thing. So let's say my base case is fine, right? I have, it's equal to 1. My recursive rule, right? My recursive step, it's still good. It's n times n minus 1 factorial, so that's all looks good. But one thing that we didn't really talk about it, but let's do so now, is the order of these two things. So imagine, and again, I'm gonna need some more space on my other side, so let me draw out this little region here. Imagine that we had these rules kind of in a different order. So imagine that I had the n factorial above the 1 factorial, right? The order of these two different rules for computing out a factorial is I just flip the order of them. Up until now, we've actually been doing something that I didn't mention. Which is, when I want to go and compute my factorial, I look at the first rule that applies to me, right? So when I was talking through the example here, I have this one, I said, okay, I'm looking for a factorial of 3, so I check to see, is that equal to factorial of 1? And it's not, so I go to factorial of n, and so on, right? So every time I was trying to figure out what rule to apply, I started at the first one and went down to the bottom one, right? That's what we've been doing so far, is always checking that order. But what happens if these would be flipped, right? What if I have n factorial equals n times n minus 1 factorial, and then 1 factorial equals 1? What if I had those flipped so that I checked the n factorial one first? Well, let's take a look at that. So let's say we had 4 factorial, and we were trying to compute the value of that. So imagine I'm going to look at this rule first. So I see n factorial, that rule applies, right? N equals 4. So I can write n 4 factorial equals 4 times 3 factorial. Okay, so far everything looks good, right? It looks like the first one we did that was correct. And then we do the same thing again, right? We look at n factorial. That applies, so I'll go ahead and rewrite that. So 4 times 3 times 2 factorial. Still looks good. Apply that rule again. 4 times 3 times 2 times 1 factorial. Still looks good. But now we're going to run into trouble. So imagine here, right, we have 4 times 3 times 2 times, and then we want to evaluate 1 factorial. Well, if these rules are in the other order, and I'm trying to figure out which rule I should apply by picking the first one that I can use, well, I look at this thing and I say, can I use the rule n factorial to compute factorial of 1? Well, n is any number, right? So I can actually use that bottom rule to compute that 1 factorial, right? If I don't first have a chance to look at this top rule, I can apply this more general rule, right? This rule up here, this one is very specific, this one is very general. And if they're in a different order, I'd use a general rule. And if I use that, what I end up doing is writing this. 2 times 0, right? So I was doing factorial of 1. So over here it says, this is going to be well, actually I end up with 1, right? This should be 1 here. That's for the end, but it's going to be 1 times factorial of 0. Let me actually clean up that just a little bit. So let's make that look a little bit better. So 4 times 3 times 2 times 1 times factorial of 0, right? Notice we didn't stop. And this will continue again, right? Let's say I want to compute the factorial of 0. Well, if I try to have this one as the first rule, then I'm going to have this. 4 times 3 times 2 times 1 times 0 times negative 1 factorial, right? This is very, very wrong, right? This is, again, a case of infinite recursion, right? I'm never going to be able to get to the end. Because my n factorial rule is so general, I never have a chance to use the 1 factorial rule, right? Because n can do everything for me. So in that case, we end up with infinite recursion. So kind of the takeaway from that is that our base case, right, our 1 factorial, that's something we always should check before we go to kind of the more general recursive step, right? We always want to make sure that we have a chance to stop, right? We need to make sure that we can stop, or we can terminate, really. That's one of the takeaways, right? We want to make sure that we're able to terminate, and we're also making progress towards it, right? Well, not only do we have the ability to hit 1 factorial, but we also need to make sure that we're doing the n minus 1 thing here in the recursive step so that we're making progress to it, right? We need to make progress to it, and we need to get there. And we need to make progress to it, and we need to actually be able to check for it. If we do those two things, then we'll be able to have a recursive function or a recursive method.